Hello and welcome to this Docker 101 course from Cloud Yuga. First thing first, this course is designed for all the beginners and the newbies who are just starting their containers and the Docker journey. This course is also for you if you just want to get a quick intro about what are containers, what is Docker, to maybe share with your teammates, with your boss and whomsoever. This course is also for you if you just want to get your hands dirty and do some hands-on, details of which I'm going to share just in a few minutes. This course is also for you if you want to use containers and Docker at work, as this is going to build the solid foundation for you. This course is completely hands-on. You can practice as you go over the content. For that, please sign up for the course using the link given on the screen. Once you are inside the course, you can explore the content. From the top right of the page, you are going to have a lab setup button, which you can click to trigger the lab. Once the lab comes up, you are going to get a terminal to work with. There you can write any commands, or you can simply copy paste from the page itself. On the page as well, we have the button of execution, which when you click is going to run the command on the page itself, and the output would come then and there itself. We also have an ID attached to the setup. So again, on the top right, you have the Open ID button, which when you click is going to open a new tab with the ID, in which you can write any kind of code, execute, and so on. We can also expose some of the instance ports for public access. Like in this case, we have opened up port 80. Which means whatever the applications are being deployed on port 80 of this instance would be available via the public URL, which are listed in the lab URL sections on the top right of a page. So if I have deployed any application on port 80, then when I click on this link, I can access that app publicly. Once you have finished the content, you can go over the final quiz and get the certificate of completion as well. My name is Nipendra Khare and I am founder of Cloud Yuga. In 2015, I authored one of the first Docker book, Docker Cookbook. Later, I also authored the first edition of the Kubernetes intro course for the CNCF on edX, which was taken by more than 200,000 learners across the globe. I am currently one of the CNCF ambassador as well. And I welcome you to this course to learn the containers and Docker in the right way. During the course, we are going to explore what are containers and why we should be using them. We would cover the differences between VMs and containers, and then explore different container runtimes. Post that, we are going to look at what is Docker and its architecture. We would then look at different Docker variants and then install Docker on our instance. Once we have Docker installed, we are going to look at different container commands like running them, stopping them, removing them, and so on. We would then look at how we can work with different container images. We would see how we can list images, how we can create images from the running containers, how we can create images from the Dockerfiles, and much more. We would then cover Docker networking basics and see how we can expose our applications for the public access. And towards the end, we are going to explore a real-world workflow of containers, using which we would see how we can take our application from dev to production. The container name has come from the shipping industry, in which we know that we have a standard box, and whatever we have to ship, we would put inside this box and then ship it. On the other side, the people would know how to handle it because it's a standard and everyone knows how to handle it across the globe. Now, in terms of IT, we can refer this particular box as a container image. Now, this container image is going to contain our application, its dependencies, runtime, and all the environment variables. So all of these things get packaged into this container image. and we can build multiple of such images. Now these images can be shipped to different environment, and then we can create containers from it. Like in this case, we have shipped our container image in the dev environment and created containers. Similarly, we can ship these container images to the prod environment and we can create the similar containers there as well. So we create container image once and then ship it to different environments like dev, production, and create the similar kind of containers on those environments. Let us now look at why one should adopt containers. In our day-to-day life, we adopt anything if it is going to save us time and money. And the same is applicable for the containers as well. On the screen, we can see that we have the similar hardware, and if we are deploying our applications on top of the VMs, then we could run only 4 full-blown VMs along with the applications on the hardware what we have. But if we move to containers, then we can run 3x more applications on the same hardware. So that is how the containers are going to save us money by packing more applications on a same hardware configuration what we used to have earlier. Now the containers are going to save us time by streamlining our entire development workflow and life cycle. So once we package our application with containers, we are sure that it is going to run irrespective of the environment we are in. And this basically makes the entire development cycle much shorter, and that is how it is going to save us time. And if we save time, eventually we are going to save more money because our development QA time is being reduced now. So that is why one should adopt containers. Let us now understand how does VMs and containers differ. When you would have first heard about containers, you may have also heard that containers are lightweight VMs, which is not true at all, and we would explore that in this particular part of the course. We create the VMs with the help of hypervisors like VirtualBox, KVM, and so on. These hypervisors communicate with our hardware to give us hardware level virtualization to create different VMs. Now these hypervisors can be installed on top of the host OS or they can skip it altogether. It depends on the hypervisor implementation. Now here we can see that we have deployed 2 VMs of Linux and 1 VM of Windows. So we can deploy different kind of OSs here. Every OS by itself is going to have its own kernel space, and then we can deploy the applications on top of the virtual machine. And with those applications, we can serve our customers. But if you look at our end goal was to deploy the applications. We took the help of virtual machines because we wanted to give every application its own isolated setup, which was not possible if I deploy all of these applications directly on the host system. As we have understood that our end goal is to deploy these applications, what if we could do it in the more effective way? And that is where the containers come into the picture. So on top of our host OS, we deploy a container runtime like containerd, which would help us run these containers. Now these containers are going to run in the independent and isolated way. With that I mean that every container is going to have its own host name, IP address, and so on. We can also control how much resource each container is going to get, like the amount of memory and the CPUs and so on. We also refer the containerization as the OS level virtualization. Let us now further dive into container runtimes. We as a user or our programs are going to communicate with the container runtimes, which eventually going to talk to the host kernel what we have to create the containers for us. Now, as there are going to be different runtimes, we need some kind of standard to communicate with our host OS, and for that community has created the Open Container Initiative or OCI standard, using which the container runtimes communicate with the underlying kernel to create the containers for us. Now there are different categories or different types of the runtimes we have. Like in this case, we have listed high and low level runtimes here. So high level runtimes communicate with the low level runtimes to create the containers. The low level runtimes are responsible only to create and remove containers, while the high level runtimes provide more functionalities, for example, doing the image build process or pulling the image and so on. So in this case, we can see the container D is our high level runtime, which communicates with the runc as the low level runtime to create the containers for us. Now, just to be clear, the containerization is a feature of the underlying kernel or the host we have. The runtimes are just way to interact with those features to create containers for us. Like in Linux and Windows, we have the feature of control group or C group and namespaces to do the resource allocation and resource isolation respectively. So for example, when we create a container and we want to allocate a fixed 2 GB RAM for our container, then the control group would implement that particular limitation. Similarly, if for our container we are requiring a unique IP address, a unique host name and so on, that is we are going to get with the namespaces feature, which is going to provide us isolation. And this isolation would be with respect to the host system and with respect to the other containers as well. Next, we have a very specialized runtime which we refer as the sandboxed container runtime. And the example of it is gvisor. As the name suggests, we want to run our container in a sandboxed environment, and we don't want these containers to kind of get access to our privileged system calls on the host system what we have. So what we do here is, in the sandbox environment, we have this gvisor component which behaves like a user kernel for the container. So container thinks that it has the entire access of the kernel via the gvisor, but then gvisor kind of controls those system calls or limit those system calls which we are going to send to the host system. So to the host kernel what we have, we only get limited system calls, and that way gvisor plays an important role to kind of control the privileged access from the container to our system. So our host system would never get the privileged access from the container what we are running there. So gvisor is very useful in cases where you just want to run any application from the internet on an environment without worrying about it. You just download the image and run it with the gvisor. The next runtime what we have is again a very specialized runtime which we refer as the virtualized container runtimes, using which our host system is going to create one VM per container using the hypervisor we have configured. Wait, what? We are creating a VM per container? Yes, that's true. And that is because of the security concern. The VM layer provides us better security than the containers in some cases, And that is why we want to have this kind of runtime. The VM which we are going to create is not going to be the full-blown VM which we are used to. It is going to be very lightweight VM to just make sure that we have that VM layer to create the containers in a more secure way. So it definitely has some use cases in certain environments and it is being used in the production now. Kata containers is an example of such virtualized runtimes which we can use to create VM per container. So I hope now you have got an idea of different runtimes what we have and how we can create containers using them. Let us now look at what is Docker. From the Docker website, Docker is an open platform for developing, shipping and running applications. Docker comes in two variants, Docker Engine and Docker Desktop. We require Docker Engine minimum to run the applications with the Docker. The Docker Engine consists of a client program called Docker, Docker daemon program on the Docker host, and the API calls using which the client can communicate to the Docker daemon. So that is the Docker Engine. Docker Desktop provides more features on top of it, like graphical control, integrate support for the Kubernetes, integrated Docker Compose, and much more. We are going to explore Docker Desktop later in the course as well. Now, here is the architecture of Docker, in which we can see that we have our client communicating to the Docker host, a Docker daemon to create containers. Now we can create containers if we have the images available locally, else the Docker is going to reach out to the default configured registry from which Docker would first download the images, and once the images are downloaded, then we can create containers from it. Docker leverages containerd to create different kind of containers. Like in this case, we can see containerd is the high level runtime, which is calling the low level runtime called runc to create the containers. Docker can also leverage containerd to create the sandbox container with the gvisor, as containerd has the shim to support the gvisor sandbox runtime. Earlier we have discussed about Kata containers as one of the runtime using which we can create lightweight VMs per container to give us more security, and that is what Docker can leverage with the help of containerd. Not just these, Docker leverages containerd to create WASM or WebAssembly based containers. WebAssembly is the new technology using which we can create even more lightweight applications than our regular containers. We are going to see the wide adoption of the WASM in the near future. I would highly recommend that you go and explore WASM or WebAssembly. Going deep into the WebAssembly is out of the scope of this particular course. So we just now got an idea how does the Docker works. Next, we are going to look at how we can install Docker and run different kind of commands on top of it. Let us now look at how we can install just the Docker engine on the Linux environment what we have here. So first of all, we are going to run the apt update command to get the meta information about the latest packages from the Ubuntu repositories. Once we have done that, we can use the apt install command to install the Docker on this Linux environment. So this would set up the Docker for us. Docker is now installed, and if I do systemctl status command, we can see that Docker is all up and running on this system. So our Docker is active and running here. Now we can run the docker version command to find out both client and server version for us. So as we can see here, we have installed the client and the server, and both of them has the version of 20.10.25. Our Docker client is going to communicate to the Docker server or Docker daemon over the REST API calls, as we have discussed earlier. We can also use the command of docker info to find out more information about both client and server. For client, we don't see much information here, but for the server, there are lot of interesting information which we can infer. Like for example, the information about the containers and images. As we can see, it is a fresh installed system. We don't have any running or stopped containers, or we don't have any images as well. It tells us about the storage driver Docker is using, what is the logging driver, and so on. We also see the network plugins which are installed by default. Then if I come down further, we can see that the default registry is configured as the DockerHub URL. So this basically points us to the default registry from where we are going to pull the images for our containers. We can also see the default Docker root directory, which is set to /var/lib/docker. And if we go to the folder of /var/lib/docker, we can see that Docker stores all the information about containers, images, network, and so on under this folder. So any information about the containers, images, network, and so on, we can find out from here. The preferred way of using Docker on the developer's workstation is by using the Docker desktop. Docker desktop is available on Mac, Windows, and Linux, so that all the developers get one consistent workflow and the view of the development cycle. Docker desktop definitely includes the Docker engine and the Docker CLI, so that all the Docker commands can run as usual on a system. But Docker desktop gives you additional features like a very nice UI to work with, support of extensions to make some of your tasks much more simpler. So for example, if you want to just visualize how the performance of containers are there in a system, you can use the respective extension. It supports the Docker Compose inbuilt into it. It also has support for inbuilt Kubernetes and much more. On the screen, you can see the Docker desktop view from my workstation. Here we have different tabs to manage containers, images, volumes, and much more. We can also manage our extensions. Like in this case, I have already installed the container watch extension. Let us now go ahead and create some containers. So I'll click on the containers tab here. I would search for the image which I want to use. Like in this case, I am searching for the Nginx image. I can pick up any of the image from here, and then once I have clicked on it, I can either first pull the image and then create the container, or I can just use this run button to start my container. Let us now go to the images tabs to explore different images. So here we can see different images what we have on the system. From the Docker desktop itself, I can pull the latest version of my image, or I can also push the images to the DockerHub as well. As of now, we have just seen very small set of operations which we can do with containers and images using the Docker desktop. Docker desktop would definitely support all the operations which we can do using the Docker engine and much more, as it has more capabilities. So I would highly recommend all the developers to use Docker desktop as the primary development environment when they use containers on their desktop. After installing Docker, let us now get our hands dirty to work with the containers and run some of the commands to create them, list them, remove them, and so on. But before I run any of the command, I would like to highlight that you may have used the commands like docker run command to create and run the containers, or you may have used the docker images command or docker build command earlier to build the container images and so on. So these commands are still valid, but in between Docker has created the management commands to help us separate out different operations. So for example, if I run this docker -- help command, I can see all the management commands here. So for example, if I want to work with the containers, I would use something like docker container run command and so on. Similarly, if I want to work with images, I would use the command like docker image and so on there. So as we are working with the containers now, we are going to use the docker container subcommand to create the containers here. So if I run the command docker container run, so this command is going to run the containers for us, in which we are specifying the -i and -t option, which says that I want to run this container interactively. Here Alpine is our image and shell is the command which I want to run as I start the container. So let me execute the command here. Now, as we don't have the Alpine image with us locally, what is happening here is the Alpine image is getting pulled from the DockerHub. As we have seen earlier, if we don't have the image locally, we are going to pull it from the DockerHub, and that is what is happening here. Now we are pulling the latest version of it. So on the DockerHub, so if I search for the Alpine image here, you can see that I have the Alpine repository here, under which I can find different version of the Alpine image, and by default the latest image we pull, and that is what has happened here. We have pulled the latest image of Alpine, and now we are inside the container because after pulling the image, the container got created. And now if I run the commands like, for example, IPA, I can see that my container has a unique IP address. Similarly, I can say that my container is going to have its own host name. It even has its own process space as well. So we can see here the shell, the program which we have run, has got the PID 1 here. So this is how the Docker uses the namespace feature of the Linux kernel to create the isolation between different programs, containers, and the host system there. Now to come out of this container, if I type exit, it is going to stop my container and bring me out. But for now, I would not do that. I'm going to press Ctrl P and the Ctrl Q combination, which is going to detach me from this container. So my container is still running in the background and I have just detached myself from it. Now if I run the docker container ls command, which lists all the running containers only. So as we can see, our container from the Alpine image is running here. And if I use the docker container ls command with the -a option, this is going to list both running and stopped containers. As we don't have any stopped container, they are not being listed. But if you had any stopped containers, they would also come here. So we have seen how we can run the container in the foreground mode earlier. Now to run the container in the background mode, we are going to use the docker container run command with the -d option, which runs the container in the background mode. Now here we are also giving a name to the container called web here, and we would use the image of Nginx with the Alpine version. So Alpine is a version here. And as you can see that we have not defined any custom command like the way we have defined sh earlier. This is because we want to run the default command as the container starts. We'll talk about this default command later with the Dockerfile section as well. For now, let us go ahead and run the container. So as we can see, this has created the container with the name of web, and I can verify it with the help of docker container ls command here. As I already had the Nginx Alpine image, it ran directly from it. Otherwise, we would have first pulled the image. So because image existed, we have got our container created very quickly. Now, if you look at the output of the docker run command, we have got this big ID. So every container is being identified by the Docker with a unique container ID. That is what we have got, which is 64 character long. But if you look at the output of docker container ls, we can see only the partial ID of it. So this is the complete ID of a given container, while this is the partial ID. And then we can also see that our container has a respective name, which is web here. So we can refer a container via its complete ID, via the partial ID, or via the name. Now we can use the docker container inspect command to find out more information about a given container. So here, let us now run the docker container inspect command. As I run the command, you would see that a lot of useful information is being spit out here, like the container ID, what is the default command that has run, which is with this combination here, what is the state of the container, is it running or not. So all kind of information about a container is coming from the inspect command of Docker. So whenever you have to find out any information about a container, just inspect it and you would get it. And if I come down further, I can find out other useful information about the container. So whenever you have to find any information about the container, just inspect it and you would get it. So for example, here I can see the IP of the container, which is available here. And if I do curl on this IP address, you would see that it is able to serve the web page of the Nginx for us. So we have got a private IP for our container, which we can access being on the system. Now to stop the container, I can use the docker container stop command. So currently, if I look at docker container ls, it is listing me all the running containers only. And if I do docker container stop, it is going to stop the web container for me. And now we would not see the web container in the running state here, as we can see. Now if I do docker container ls-a, we would see that our container web is in the stopped state here. As we can see, it is exited 15 seconds ago. Now to remove a container, I can use a command called docker container rm web. So this command, docker container rm, is going to remove the container for me. So let us go ahead and remove the container here. And our container is being removed. And if I do docker container ls-a, you would see there is no container with the name of web because we have just removed it. So here we have seen some of the basic operations with the containers. But before I move on to the image operations, I would like to highlight a very important property about containers. And that is, we can create multiple containers from the same image. Like in this case, we have the Alpine as our base image, from which we have created multiple containers. Now all of these containers are going to mount the base image in the read-only mode only. When we create a container, every container gets its own temporary storage, and whatever we are writing on that container is being written on that temporary storage only. Our base image is always intact. Now, when you remove the container completely from the system, this temporary storage layer also gets removed. So be careful not to write any content which you want to persist in this temporary storage. We would see later how we can take this temporary layer and convert into the image layer in the next section when we work with the images. Let us now perform different operations with our container images. The first one we would look here is how we are going to pull the images. Earlier, our image got pulled because we have ran the container, and because we did not had images, our images got pulled from the DockerHub. Now, if I want to pull the images manually, I can use the docker image pull command, or in the old way docker pull command to get our image here. So like here in this case, we are saying pull the image of Nginx with the version of latest. So I talked briefly about it earlier as well, that our images can have different versions which we refer them as tags. So here we have the latest tag which is defined here. So if we go to a DockerHub, we can see that each image can have different tags here, and we can choose to download the specific tag for us. So here we are downloading the Nginx image with the latest tag. This is the default tag as well. So if you don't specify, then also the latest tag image would be downloaded. So we can see here that it is downloading the latest tag by default for the Nginx. Let us go here and search for the Nginx images or Nginx repository here. So we are now into the Nginx repository, and here we can find different tags which can be associated with the Nginx image here. So now we can run the command docker image pull colon, and then we can specify the tag which we are interested in. So we are saying we would download the 1-perl here. So I'll do 1-perl, and now this particular image with the tag 1-perl would be downloaded. And if I do docker image ls, we can see here with docker image ls, we can list all the images what we have on the system. So we already had these two images earlier. We have just downloaded these two images right now, which are with the tag of latest and 1-perl. Also, as we had the container ID, we also have the image IDs here. So we can download our image via the image name like the one we have used earlier, or we can choose to use a specific image ID as well. So I can say as well that give me the image of docker image pull and the specific image ID as well. So this would also download the respective image from the given registry. If you had paid attention to the docker image ls output, you would have noticed that none of the header says image name. So what is the complete image name? It is mentioning about a repository and the tag. With respect to the Docker, the complete image name consists of the registry name slash the repository name, then colon the tag. This is the complete image name. So if we are to look at the complete image name of the Nginx Alpine, then it is going to be the Docker registry URL slash repository, which is Nginx, and then the Alpine version here. And if you recall, in the Docker info output, we have seen the default registry location here. So for this particular image, the complete name is going to be the registry name, then the repository name, and then colon the tag name. If we had to download the image from the private registry, then I would say like docker image pull private registry URL, then the repository name and the version or the tag there. That is how I would download the image from the private registry. The way we have inspected our containers earlier, we can also inspect our images. Like in this case, we are inspecting the image nginx with the latest tag. And here we can find out the complete image ID. We can find out its repo digest as well. Then we can find out what are the different layers which makes this particular image. So in Docker or in container in general, we start with a base image, then we make some changes, we make a new layer and so on. This would become more clear just in few minutes. As we discussed earlier, whenever we create a container gets a temporary storage to work with. Whatever changes we are going to make or whatever writes we would do, it would be in this temporary storage only. And when we remove the container, the content of this temporary storage is also gone, which means we cannot have any persistent data in this temporary storage. But what if I want to save the container state in some way? So for example, if you have taken a base Ubuntu image, you have installed some software, you have cloned your source code, compiled it and made the binary ready for others to consume. Now, if you can't save that state, it is not going to be of any use. And that is where we can convert this temporary storage what we have into a image layer. So what we can do is we can commit this temporary storage and create a new image out of it. So what we have done is we had the base image. On top of it, we have committed the layer from the previous step, and this would give us a new image which says that I have the change what I have done in the last step, and I also refer to the base Alpine image. And then we can create further containers on top of it. And that is how the overall committing process works to create new images for us. Let us now do the hands-on with this. So we would now create a container with the name of myalpine here. And let's create some files into it. Let's say we run the date command and create two files here, file 1 and file 2. We would now detach ourselves from this particular container with the Control P and the Control Q command. So now we have that temporary storage in which we have this content. And to verify that, I can use the Docker container diff command to find out what changes have happened from the base layer what we have. So if I do Docker container diff and myalpine, which is my container name, we can see here it says that we have added two files here, file 1 and file 2, which we have done in the previous step. Then a history file has been added by the system itself, and then we have changed our /root directory. So this is what is in that temporary layer which I was mentioning earlier. We can now use the Docker container commit command to create a new image from the running container which we have. Like in this case, we have the myalpine as our container name, and I want to create the image with the name of my image. By default, it is going to get the latest tag only. So let me go ahead and run the command, and this would create the image for me. And now if I do docker image ls, we can see we have got a new image with the tag of latest, and the name of the image is my image here. We can now create a container from it, and in that we would find out our files, file 1 and file 2, because we are now using the new image. So let me run the container. So docker container run -it, my image is the image name and the tag and the shell command which I want to run. So as you can see that we have now those file 1 and file 2 inside this new container, because these files were part of the image what we have built earlier. So this is how we can create images from the running containers what we have. We would have to create our container images on a regular basis. So for example, if our developer does a code commit, we may want to generate an image from it and then take it for the test and the deployment purpose. Now, nobody is going to sit down manually and do the process what we have seen earlier, in which we create a container from the base image, make changes, then do a commit, and so on. So we would be needing some kind of automated way to ease this process. And that is where the Docker file comes into the picture. In the Docker file, we write down our instructions with the argument, and then we would use the Docker image build command to execute these instructions one by one to create the resulting image. Like in this case, you can see we have a Docker file with 5 lines here, in which we start with the base image Python:3. So from is the instruction which tells you what base image you want to have. Then in the second instruction, we are saying copy dot means current folder. So we are saying whatever is in your current folder, copy it inside the image under /usr/src/f folder, or whatever folder you may have. So we copy our content into the resulting folder in the second step, which creates our layer. Now, every time whenever Docker is executing this build process, at every step it is going to create a container from the previous step. Like in this case, it is going to create a container from the base image, then perform the step of the copy instructions, and then commit that container and make a new layer out of it. So that's how we get the layer 1. Now for the layer 2, we would create a container from the layer 1, perform our step in which we are doing the apt update command, and then once that happens, we are going to again commit. And that is how the step-by-step process happens. So similarly, we would do the step 4. In the step 5, we have the cmd instruction, which basically sets the default command which we want to run as the container starts. So cmd is our runtime instruction, which runs as we run the container, while from copy run, these are the build time instructions which we use to build our image. So with this information, let us now go ahead and do some hands-on. The first example what we have is going to help us create the similar image what we have seen earlier, in which we created the image from a running container. So here we have a Docker file. In this Docker file, we are going to have 3 instructions to create our image. The first instruction here to define the base image. Then we have 2 run instructions to create 2 files, file 1 and file 2. You can think of run instruction similar to the bash commands what we would run when we do some operations on a regular instance. So we are defining the run instructions to create 2 files here. Now once we have this Docker file with us, we can now create, or we can now build a new image here. So for this purpose, we are using the Docker image build command, and we are using the -t option to define our image name. And with this dot, we define our build context, which is the current folder. So for example, if you want to build with respect to a different folder, we can define a folder name here, which would have all the build context and the supporting file which we would need. But in the current case, we have our Docker file in the current folder only. That is why this dot is being defined. So here we can see that we are performing 3 steps here. Step 1 of 3, step 2 of 3, and step 3 of 3. In the step 1, we get our base image with this image ID. Then in the step 2, we are going to create a container from this image. In that container, we perform our date command to generate the file 1. Then we commit and get the image with this image ID. Then in the step 3, we are going to take this image to create a new container. In that container, we would perform our date command to create file 2. Then we would commit and get the new image ID. And that is how the build process works. As our image is now being built, we can create a container from it, and then get the content of file 1 and file 2, whatever we have created just now. Now typically these Docker files get stored along with the source code what we have. So as you can see here, we have this RSVP app repo, and in this we have our Docker file. Now let me open this Docker file, and as you can see here, we are having this copy instruction using which we copy all of our code inside the image so that we can perform the respective operations there. So for our second demo, we are going to create an SRC folder in which we are going to have two programs. So like now we have the SRC folder in which we would be having two programs, prog1.py and prog2.py here. Now in our Docker file, we are going to have the copy instructions to copy our source code inside the /f folder of the image. So let us now go ahead and modify our Docker file and add the fourth line here to do the copy. And now we can rebuild our image, and you can see that our image is now being built and our code is also being copied inside the /f folder. And now while running the container, I can define my custom command. So like in this case, we are saying, as you run the container, run the command of ls/app here. So as our container runs, we are going to say that the default command for this container is to list the file in /app, and that's it. So now our container starts and it just lists those two files. That's it. That was the default command I have set up. Now, for example, I don't want even this command to be specified. I want some command to run by default as my container starts. So for that purpose, we are going to have the cmd instruction. So now in this case, what we are doing, we are saying that configure our container or configure our image such that whenever the container runs, it is going to run by default the Python prog1.py program, which is inside the /app folder. So let us now open our Docker file and add the fifth line here to set up the default command to run as we run our container from that image which we are building. So let us now go ahead and again build our image. So we would change the different tag here. So our image is now being built, and now when we create the container, you would see that the default command would run and it would execute the program 1 what we have inside the /f folder of our image. Let us now go ahead and look at the Docker file of Nginx. So for that, we can go to DockerHub and click on any of the respective version link here, and this would open the Docker file for us. So as we can see here, we have the instructions like from, label, env. So we have seen only few of them earlier, but here you can see more instructions. So from is again the base image. Label is nothing but you want to set up some key value pair. Then env to set the environment variables. Then we have the run instruction here. But as you can see here, we are combining multiple run instructions with these AND operations. So as we know, at every instruction which we run, it is going to create a layer for us. Now, if we have multiple run instructions, it is going to create n number of layers. But to kind of shorten or to reduce the number of layers, we can combine multiple run instructions into one. And then we have bunch of copy instructions which we already talked about. The entry point is another runtime instruction which works with the cmd here. Then we have the expose instruction to listen on port 80 for this particular container. Similarly, you can look at the Docker file of different softwares. You can search for the image and then look at its Docker files. For more information, you can always look at the Docker's documentation for the Docker file. Once we have created these images, we would want to share these images with others. One approach is to generate a tar file for each of these images and share it by means of SCP or others. But that is not a good approach. The good approach is going to be take these images and then push it to a registry like DockerHub and then have others to download it from. We can also push these images to private registries which we can configure. For now, let us see how we can push these images to DockerHub. So our DockerHub registry is configured by default as we know. But we need to first log into DockerHub from the Docker CLI what we have. And for that we can use the Docker login command. But before that, you have to make sure that you have an account on DockerHub. If you don't have, then you can simply go to DockerHub and then register here. As I already have an account, I can run the command of Docker login. I'll give my username, the respective password. And now, as you can see, I am logged into the DockerHub from this machine. So if I do Docker info, you would now see that it is also listing the username which I am using here to connect with the DockerHub. Now let us try to push the image what we have on this system. So we would try to push the image, my image, with the tag of cmd. As I try to push, it is giving me the permission denied error. And this is happening because we are trying to push the image on the root of the DockerHub. We should actually push this image into our own account. So for example, if I log into the DockerHub, I can see my account and I should be pushing the image inside my own workspace there. So this is my username for the DockerHub and I should be pushing these images under this. So as you can see, I need to make sure that while I am pushing the image, I would prefix the image with my username. Now to prefix the username with our image, we are going to use the docker image tag command. And in this case, I am giving my image name which I have created earlier along with my username of the DockerHub / the image name what we have here. So once we run this command, it is going to tag my image with the right name there. And if I do docker image ls, you can see that I have another image with the name of nCurry / my image and the tag is cmd here. Now this image is like a sibling to the previous one. As you can see, the image ID remains the same in both the cases. Now let us try to push the image. And as you can see, the image is now getting pushed to the DockerHub. And if I go to my account inside DockerHub, I can see that this image is being pushed recently. Let it finish. It is now pushed. And if I go and refresh this page, you can see here my image just got pushed on the DockerHub. Now if I have to push this image to the private registry, then I am going to add the registry name before the image name what we have. So as you can see, now I am pushing the image into a private registry with the name of registry.clouddigger.guru, then / my username, then / the repository name, the tag. So this is how we can push the image to the private registry as well. Let us now look at how does the networking works for the containers we create with Docker. So when we install the Docker for the first time with the default configuration, Docker creates a software bridge using which it can connect to different containers. Then this bridge also connect to the network interface we have to send the traffic in and out of the host system. Here we can see that we don't have any containers running on the system right now. And if I run the IPA command, I can see that we have this Docker 0 bridge, which is connected to the network interface what we have. The IP address of the bridge is 172.17.0.1 here. When Docker creates a container using the Docker commands, it also creates a connection between the container and the software bridge it has created earlier. We can think of it, Docker is adding a virtual LAN cable between them, in which one endpoint of the virtual LAN cable goes to the bridge and the other endpoint goes to the container. And via this particular bridge, our container can communicate to the external world, and similarly external world can also send the traffic to the container what we have. As we create more containers, the Docker is going to create the similar virtual LAN cables for each of those containers, and these containers can communicate among themselves via this Docker bridge only. Let us now create a container with the Docker command here. And now we can see that we have another interface which was not there earlier. And this is the endpoint of the virtual LAN cable to the bridge side. Now let me get inside the web container which we created with the docker container exec command and run the IP command inside that. As I run it, I'm going to see the other endpoint of the virtual LAN cable, and we can see here there is this ETH0 interface, which is the other endpoint of the virtual LAN cable, which is connecting the container with the Docker 0 bridge. I can create more containers, and as we create more containers, we would see that more interfaces are getting created at the bridge level, and similarly each container would have a respective internal interface as well. So if I create more containers, let's say with the web1 name and then web2, we would see now that on the host system we would be having two additional interfaces. So as we can see now, because we have three containers, we have got three interfaces here. This was there previously, we just added two of them right now. Now if I remove the containers, automatically these interfaces would also go away. So let me now remove the containers which we created. So if I do docker container rm web2, I can use the force flag to remove them without stopping. Similarly, I would remove the web1 as well. And now we would see that there is going to be only one interface at the host side because we are left with only one container here. So this is how the Docker configures the networking for our containers by default. As we are running our Nginx application inside the web container, let us now see how we can access it. To access the Nginx web server, we would require the endpoint's IP address, which we can of course get from the exec command we ran earlier. So with the exec command to the web container, we can see that the IP address of this container is 172.17.0.2 here. We can also use the docker container inspect command to inspect the web container and find the IP address as well. Now, as we have the IP address, let us simply do a curl on this IP address. And as we do the curl, we can see that we get the reply from our web server, which is serving on port 80, and it shows us the default index page what we have here. Now the IP what we had for the container which we have used, now this IP is a private IP. We cannot use this IP address to access the application from the outside world. To access the applications from the outside world, we have to do the port mapping, in which we map a port on the host system with the port of the container. Like in this case, we are saying map the port 80 of the host system with the container port of 8080 for the second container. Similarly, we can map another port, like in this case port 9000 with the application running on the container 1 here. Do remember that you cannot use the same port number on the host to map different containers. One host port can map only to one of the application running inside the container what we have. For the hands-on, here we are creating the web 1 container, and with the -p option we are mapping port 9000 of the host system with the port 80 of the container which we are going to create just now from the nginx image. So let us now create this container here. This creates the container for us, and if I do docker container ls, we can see that we have got our web 1 container running here. And for the web 1 container, we have the mapping here saying that if you hit your host system on port 9000, you would go to the port 80 of the container. So we can find out the IP address of our host system with the IPA command. This is going to give us the IP of the host system. And then we can do the curl our host IP and the port 9000. And this is how we are going to access our applications from the outside world. So our end users would know our host IP address, and if they access it on the port 9000, they would come to our container on port 80. In the second example, we are configuring that for the web2 container, map the port 80 of the host system with the port 80 of the container. So as I run the command, now we have a special setting for this kind of setup. So on the right hand side, we can see that we have this lab URL section in which we have this URL app-port-80. So whenever we are going to hit this app-port-80 URL, it is going to hit our host on port 80, and from there we would eventually go to our container, which means though we have deployed our container inside this VM, I can access it publicly. So let me click on this link, and we can see that our welcome to nginx page is coming here. So this is how we can expose our applications publicly to the outside world. And here is the Docker container ls output, in which we can see that we are mapping the port 80 of the host with the port 80 of the container. So this is how we can expose our applications running inside the container to the outside world. Let us now look at one of the workflow with containers in the real world. So on the local development environment, the developer can have the Docker desktop or the Docker engine installed, using which the developer can do the development with the IDE like Visual Studio Code. Tools like Visual Studio Code has many different extensions to manage containers. Like in this case, we can see there are some of the Docker extensions, and then we would be having some of the Kubernetes extensions as well. So using which we can easily work with the containers. So for example, if I look at the command line of the Visual Studio Code and type Docker, you can see here I can find many subcommands of Docker within the IDE itself. So for example, if I do Docker inspect, then I can select individual containers here, and then whatever the containers I am running here, I would choose one of it. And as you can see, it is now giving me the output of the Docker container inspect here. We can also use the Docker and the Kubernetes tabs on the left hand side to work with them directly from here as well. So now there is very tight integration between the IDE and the Docker, which would eventually help the developer do the development faster and then take it to the next step. The next step would be here to commit our code into the source code repositories with the tools like GitHub. Then we can use our CI tools like Jenkins to continuously poll for the change in our source code. And if there is a change, Jenkins can build a container image from it and then run test cases against it. Once our CI process completes, we can take our container images and push them into the container registry like DockerHub. Then these images can be pulled via the deployment tools like Kubernetes and run the applications from them. So this is how a real world workflow with containers looks like. And as you can see, containers play a very important role from the development to the production. So with that, we come to the end of this particular course, but I'm sure this would have given you the right start for your containers, Docker and Kubernetes journey. Do subscribe to the channel if you haven't and share about this course within your network. Also, check out our flagship Cloud Engineer Bootcamp program, which can make you ready for internships and jobs in just 3 months. All the best and happy learning.